It's our great honor to present this project to you. Our topic is about air visibility recognition. The presentation will be shown in these four parts. Let me just briefly introduce in the beginning. As we all know, environmental problems are getting increasingly difficult nowadays. When it comes about the air visibility has a great influence on our lives. The air visibility in a low level makes people on the road hard to find their ways and even cause accidents. In this term, our team decided to carry out a research about a method to recognize the level of air visibility based on a machine learning method we had learned about. Currently, people using instrumental measurements and visual measurements as the two common methods. For one thing, instrumental method has the weakness of complicated option, expensive costs, and high requirements for surrounding environments. For another, the visual method highly relies on the subjectivity of human beings. With the rapid development of image processing technologies, a large number of techniques have been proposed to identify the level of air visibility. For example, using feature points, screen depth, ROI, and their combination. These methods thus improve efficiency. However, still exists lots of problems, such as currency is highly dependent on the currency of our ROI extraction, limited by acquisition template. Under a poor visibility, it is very difficult to distinguishing the road and the sky. In order to overcome these shortcomings, we are trying to apply what we learned, SVM, which is based on an optimal binary tree to get a better performance. SVM is originally introduced for binary classification problem. For the multi-classification problem, we can classify all categories into two subcategories, then continue classify them into two secondary subcategories. This process keeps going until the entire individual categories is finished, so that a multi-classifier can be constructed to achieve multi-classification. SVM using a curtain combination scheme. At present, the multi-classification SVM are mainly constructed by one-to-one method and one-to-many method. One-to-one method have inseparable regions in classification, and one-to-many method has an unsatisfying performance. Therefore, we use a multi-classification SVM based on binary tree, which is as the figure shown.
Now let's talk about the method we used. The visibility recognition method based on SVM can be divided into four steps: ROI, the ROI extraction, image processing, feature value extraction, and model training. The flowchart is shown in the picture in this page. First, let's take a look at the ROI extraction. We used silence map-based ROI extraction, which generally introduces a silence map through a visual attention model. It combines the image foreground and background information and uses image segmentation method to achieve extraction. Firstly, Fourier transform is performed to obtain the frequency domain of the image and calculate the amplitude spectrum and phase spectrum. Finally, the log spectrum is linearly filtered by using a spatial filter. The difference between the log spectrum and the processed amplitude spectrum is defined as the radar spectrum, and it is expressed by the function on the top of this page. To get better results, the unprocessed image is linearly filtered by using an 8x8 Gaussian filter, and then normalized to get the final silence map. Function 2 shows this process. Next, the silence map is binarized by the Austrian segmentation algorithm. Then the binary image is divided into a plurality of squares with 50 pixels multiply 15 pixels. The square with the largest number of the silence points is selected as the final silence region. The results of the selection are shown in the picture in this page. Now let's take a look at image processing. And the first step is expansion and erosion. Expansion can fill the small holes in image and small concaves at the edge of image, thereby remove noises in the target area. The meaningless objects and noises can be removed by erosion. The results of the four kinds of air visibility levels are shown in this page. Then is extraction of feature values. The feature values of the processed images are extracted, including edge features, local contrast features, and global transmittance. The RGB 3-channel transmittance is based on the dark channel priori server, which is shown as the three functions in this page. Function 1 helps us to set the low value pixels value to 0. Function 2 shows a commonly used digital fog image model, and function 3 shows that, based on above functions, how we can get the transmittance. Then is the edge detection. We use Sobel operator for edge detection. The calculated local gradient value is a vector. The absolute value of it is used as the gradient amplitude, and the global average gradient value of the image is used as the gradient feature value, which is defined by the function in this page. Before extracting the feature value, it's necessary to enhance the contrast of the image to improve the imaging accuracy. The process of local contrast extraction is shown as a function in the right of this page.
The results of the image feature values extracted from a part of the dataset are shown in this table. According to the above method, from this table, the edge feature values and the local contrast feature values of the images are different between different air visibility levels, while the transmittance value of RGB channels are slightly different. The transmittance values of RGB in the same image are almost the same. In our project, air visibility is classified into 4 levels: good air quality, heavy pollution, mild pollution, and moderate pollution, which are Class 1, Class 2, Class 3, and Class 4. So a 2-layer optimal binary tree is constructed. The SVM 1, 2, and 3, 4 on the first layer is to recognize Class 1, 2, and Class 3, 4. And in the second layer, SVM 1 and 2 recognize Class 1 and Class 2, while SVM 3 and 4 recognize Class 3 and Class 4. The categories under each SVM are selected according to the maximum threshold interval. The maximum branch interval under each node can effectively reduce the error of classification and recognition. The process of recognition of the air visibility level is first extract the feature vectors of the images of 4 visibility levels. First, start from the root node 1. Calculate the SVM and judge the next destination according to the output value. If the visibility level of image is Class 1 or Class 2, then go to the left leaf node of layer 2, and if the visibility level belongs to Class 3 or Class 4, then go to the right leaf node of layer 2. Second, Second, go to the left leaf node. Calculate the classifier. If the result of the air visibility level is positive, it belongs to class 1. Otherwise, it belongs to class 2. And last, go to the right leaf node. Calculate the classifier. If the result of this air visibility level is positive, it belongs to class 3. Otherwise, it belongs to class 4. And next part is the results. In the experiment, 50 images were randomly selected from each set of 75 images, and a total of 200 images were used as training samples. The remaining 25 images of each visibility level were used as test samples, with a total of 100 test samples. We use the optimal binary tree SVM model to recognize and classify the images. In this model, the inner product kernel function of each optimal binary tree classifier is this. The kernel weight theta and the error penalty parameter C of the kernel function were adjusted by the cross validation of the sample set at each node to obtain the optimal parameters. The classification and recognition results are shown in this table. In the model of the two-layer optimal binary tree SVM, the root node classifier SVM 1, 2, and 3, 4 on the first layer achieved the recognition accuracy of 96, 100, 96, and 92% for good air quality and heavy pollution, mild pollution, and moderate pollution. The leaf node classifier SVM 1 and 2 on the second layer achieved the recognition accuracy of 92 and 100% for good air quality and heavy pollution. The leaf node classifier SVM 3 and 4 achieved the 92 and 88% for mild pollution and moderate pollution. In summary, the recognition accuracies of air visibility level by the proposed method were 92, 92, 88, and 100% for good air quality, mild pollution, moderate pollution, and heavy pollution, with an average recognition accuracy of 93%. We also made a comparison between our method and one-to-one SVM and as well as one-to-many SVM method. Both the two traditional methods use the same video basis kernel function. The one-to-one SVM and one-to-many SVM had a total of 4 classifiers. In this experiment, both the training set and the test set were the same. The training time and the recognition accuracy of the 3 different methods is shown in this. The training time was 6.5, 3.7, and 6 seconds. The recognition accuracy was 88, 90, and 93%. Our method had a higher recognition accuracy and a shorter training time. The reason our method was shorter is that our method adopted the structure of optimal binary tree, which reduced the number of required SVM classifier, so shortening the time required for training samples.
To sum up and draw conclusions, using the saliency map acquired in the frequency domain of the image, the ROI extracted by the saliency region is evident in the image, which can fully reflect the features of the image, so that the feature values extracted in the ROI can be easily distinguished. Accordingly, we construct a model for recognizing air visibility level based on the optimal binary tree SVM. After the calculation of optimal binary tree and 3 SVMs, 4 air visibility levels can be recognized. Combined with the cross-validation method, the recognized occurrence of good air quality, mild pollution, moderate pollution, and heavy pollution are 92, 92, 88, and 100%, with an average recognition accuracy of 93%. Therefore, this method is able to recognize the level of air visibility in a relatively accurate way. That's all. Thanks for your listening.